So let's welcome Heather Christensen.
Hi, my name is Heather. I'm working with Jim in the Gamma Lab here, and I'm talking about radon risk mapping using gamma ray spectrometry and social vulnerability. Okay, so radon is a colorless, odorless, inert radioactive gas, and it's a daughter isotope of uranium-238. And radon can affect us in many ways, into our homes, into our groundwater, but we care about all of this because radon is a carcinogen. It is the second leading cause of lung cancer in the US. It's second only to smoking cigarettes. And radon causes more deaths per year than drunk driving, falls in the homes, drowning, and home fires. So radon is a very serious issue. However, our population here in the US just isn't very aware of it. So research in radon, we're going to start with the Gunderson and Schumann paper in 1996. So in this paper, they talked about how different rocks have elements within the uranium decay series, such as granites and carbonaceous black shales. And as these rocks are deformed or sheared or even just like existing, they can release these elements that are in the decay series out, and then gas can percolate up through the soil or into the groundwater and expose itself to the humans. So this paper talks mostly about the cracks in the bedrock. In North Carolina, my study area, most of the published papers about radon have to do with radon in groundwater. So as this groundwater goes through the cracks in the bedrock, you can pick up this radon, and then as you pull it in through well water or you shower in it, you get exposed to this radon. And so a lot of the papers talk about the different cancers caused by this exposure from groundwater. However, there hasn't really been much looked into with indoor radon in North Carolina and the soil, which is the next way that radon can enter into your home. And so the William Ray Gamma Lab focuses a lot on this in the sediment here in Williamsburg, and I'm also focusing on the sediment in North Carolina. So there are different grains in the soil and also diffusion up from the bedrock of this radon gas, and it can enter into your home as the weight of the house sits into the soil. The foundation kind of creates a vacuum, sucking that gas in through cracks in the foundation and in the walls and everything, and can collect this radon gas within your basements. So when it comes to mapping this risk, this is the EPA map of radon risk zones, and you can see everything that's red is high risk and everything that's yellow is low risk. And there's a bunch of generalization across geological ranges here, or geographic ranges here. You can see like the entire Atlantic coastal plain is yellow, Wyoming is just red. So we can see here that there's a lot of generalization across wide ranges of the US. And if we overlay, again, that Gunderson and Schumann paper where they mapped the bedrock potential of radon, it's pretty much an exact transfer. So wherever you see high potential here in black, it's red in the EPA map. And everywhere that it's like white or low potential, it's yellow in the EPA map. And so the entire Atlantic coastal plain, I'm pointing with my finger like you can see it, the entire Atlantic coastal plain is generalized as low risk, both in the EPA map and in this Gunderson and Schumann paper. However, the William Ray Gamma Lab has shown that within Williamsburg, this was done by Dorian Miller last year, they looked at sediment cores within the surrounding area and found that the base of the Yorktown Formation had high levels of gamma radiation. And so that shows a lot more local variability in radon risk than indicated by the EPA map and the Gunderson and Schumann paper. So, I'm screen sharing. So anyway, in this map right here, all of these parameters that show red, this is the elevation parameter for the base of the Yorktown Formation. And so any house that's built within these red areas is built within the base of the Yorktown Formation where we found there to be high levels of radon, and thus they are in a high risk area. So that's a way that we can show higher resolution radon risk mapping in this area. Going into my specialty in this section is adding a social vulnerability dimension, because in both the EPA map and even in the most recent Williamsburg map, the risk is generalized across the population. It's based just on geography, and it doesn't take into account the people that live in this area and how different populations can be disproportionately impacted by radon. So many factors could influence this, and we can look at biological risk factors, factors that increase the duration of exposure, and also factors that can impact someone's access to public health information regarding radon. And I go in depth into each of these in my thesis, but just to do a quick overview. So when it comes to lung cancer being the main thing that if you smoke, you are significantly more likely to get lung cancer from radon exposure. And many populations are a lot more likely to smoke, such as those from low socioeconomic status and certain racial and ethnic minority groups. Furthermore, different ages, so there are particularly young groups like children and elderly populations are also more at risk for radon's health effects for different reasons. Disability status is a pretty complicated one to go into, but there are multiple different factors such as pre-existing health conditions that can interact or make you more susceptible, all the way up to mobility limitations, increasing the duration of exposure by keeping you in the home. So there's a bunch of different factors going on there. And then when it comes to radon literacy, as you can see, these are all different public health education information things about radon in your home or in your water. They're all in English, and the majority of them are in English across the US. And if English is not your first language, you are missing out on a lot of this educational material. And if you don't know it's a problem, you're not going to know to test for it or mitigate for it. And there's also further information that I'm looking into, particularly on landlord-tenant interactions and how someone's citizenship status or primary language can impact the communication or their rights with their landlord, and thus impact their communication from landlord to tenant about what risks they might be signing up for when they go to rent a home. So my site, I went down into the North Carolina coastal plain for a bunch of reasons. First of all, like I said earlier, there's a big knowledge gap there when it comes to radon from the sediment, and indoor radon, it's mostly focused on the groundwater. So I wanted to try to fill that knowledge gap a little. Also, that Yorktown formation that we talked about here in Williamsburg that has high radon levels extends down into the North Carolina coastal plain. So I figured that was a good place to start. Also, it's characterized, just like the rest of the Atlantic coastal plain, as low risk by the EPA, but these at-home radon tests displayed here show that a significant number of the counties within the North Carolina coastal plain have high measurements or greater than 4 picocuries per liter of indoor radon. So greater than 4 puts you at a higher risk for lung cancer, and some of the counties in here reported measurements as high as 54 picocuries per liter. So we're seeing that there's an inconsistency between the generalized EPA rating for this area and what we're finding in these actual home measurements. And then finally, I looked into social vulnerability information in this area. This is indicating that a lot of the counties within my study area, more than 30% of the population lives below the poverty line. And I go into other factors having to do with social vulnerability once I chose this area, but this helped me guide my site selection. So I have 2 cores, one in Nash County and one in Edgecombe County, both within the North Carolina coastal plain. So my research objectives were twofold. So one, I want to add to the assessment of radon risk in the North Carolina coastal plain by measuring uranium and radium within these sediment cores. And then second, I want to modify these existing mapping methods to, one, increase the resolution through elevation parameters based off of local measurements, but then also including the influence of social vulnerability so we can prevent from generalizing both across a wide geographic region and also generalizing across a population. So my first objective when it comes to these measurements is everything that I did with my sediment cores. So I'll go through my methods, my results, and my interpretations. So I got my 2 sediment cores from the North Carolina Geologic Survey, and they came to me in a bunch of little baggies like this, but they were pretty fresh and they were still wet. And so the first thing I had to do was freeze dry them. And then when they come out of the freeze dryer, especially the ones that have a lot more clay, they kind of come out like a solid brick. So I had hit them with a hammer a lot. And then I was able to pack them into these little containers here, get their mass, tape them a bunch with electrical tape, and dip them in wax 4 times. And this was to seal it all in, get it into a perfect geometric unit, and allow radon gas to accumulate inside, sealed within, to then put it in the intrinsic germanium detector, which is where I did my gamma ray spectrometry. So I'll talk you through this really quickly, but my 2 cores didn't overlap in elevation, but they went up pretty much right up against each other in elevation. So it was great because I was able to see a wide range of elevations by comparing the 2. So I was able to stack them on top of each other. And so elevation is here, and each of these are my radium-226 measurements. And so each one of these is a little baggie or a sample that I ran. And in order to generalize, like we have all of these, but what does any of it mean in comparison to crustal averages? Because crustal average is not 0. So I went to an Agreement et al. Paper also in 1996, which is our best comparison for crustal averages of these measurements, radium and uranium in the East Coast or in the Eastern US. So there are 12 sites, and they reported their measurements for all of these sites for radium, uranium, the comparison between the two. And so I took the mean and standard deviation of these and decided to overlay that information on top of my map. So on top of my graph. So this area is the mean plus or minus 1 standard deviation. So everything in orange is average, according to like the crustal averages reporting in this paper. This is everything above 1 standard deviation. This is everything below. So we can see from this that there are multiple elevations that have radium measurements significantly higher than the crustal average. And yeah, that's right here. And you can see this is important because when we're going into radium, we're looking at the exact source of this radon. So we're measuring radium-226 because in this decay series, you can see if we have radium, it is producing the radon. And so we go straight to the source of the radon to measure the radon potential, which is the radium. Then when we compare our radium to uranium ratio, as we can see here, uranium decays down to radium, which eventually decays down to radon. And so when we're comparing radium to uranium at equilibrium, we're assuming that there would be an approximately 1-to-1 ratio, or it would show up as 1 on this graph of uranium to radium. So it's just going in a straight line, uranium down to radium, and then continually decaying. However, we see a significant enrichment in radium in majority of the elevations of my cores. And so this means a few things. It means that within each sample, there is more radium than uranium. So the radium that is in that sample has to be coming from somewhere other than the uranium in that sample. So this means there is a mobility of this radium. It means it must be coming from somewhere else. And if the radium is mobile, it means that these elements are not locked within things like quartz crystals or something where, sure, we detect its presence, but it's not releasing this radon gas. But since it is mobile, it means that it's free. Maybe it's tagged onto some clay or something, and it can be released. And so high measurements of radium plus an enrichment of radium indicating mobility goes together to high radium and thus high radon potential. So that was my sediment cores, and now going into my mapping methods. So I want to, again, increase resolution by using these elevation parameters from my cores and then overlay my social vulnerability data. So I decided to make a topographic map of my study area using digital elevation models from North Carolina State University. And you can see these are my 2 cores and my 2 counties of interest. And then I included some counties surrounding because I wanted to give like a better idea of where this topography continues within this area. So I included these 2 counties as well. So you could kind of see that the red and the green carries down. And it's important to note that the elevation included in my cores goes from 140 to about 20 feet, and this goes up to about 360, and down here is around like 15. I know it says negative 130. There's like one really deep canyon in here. Oops, that kind of messed up the scale. But anyway, so that means that when I map my elevations from these cores, there are going to be some areas that are outside of the parameters of my cores, and so I just map them as gray or no data. So wherever I had ranges of elevation within each of these groups, so orange, red, or yellow, I then filtered this raster to become that color. So everywhere from maybe about 140 to like 125, I used the actual numbers, I didn't estimate, became orange. And then it continued down with these as well, and created this. And according to the EPA map, this is all yellow, but this is very clearly not yellow. So just from like base level interpretation of this map using just the elevation parameters from those 2 cores, you can see that we need to use the local geology and the local sediment radium levels to map this, because if we generalize all the way across regional geology, we're leaving out a bunch of potential high risk areas. So next, including my social vulnerability. So this is a social vulnerability index. This is made by the CDC using US Census Bureau data. And there are 4 themes listed here. And each of these themes has multiple factors that contribute to its overall ranking. And I went into a couple of these in the beginning when I was telling you about social vulnerability. And I go really in depth into each of these in my thesis. But a couple of these do not increase radon potential. They either don't affect it or they kind of decrease it. And so I decided to leave them out because my goal, just within the amount of time I have, is to just take my social vulnerability rankings, overlay them in anything that will increase risk, and then increase my overall layers because of that. So that's why I'm using just things that increase radon risk. So everything in housing type and transportation in here, usually these are used to for emergencies or natural disasters to best distribute help. And so that's why there's this massive housing type and transportation theme. I decided to leave it out since it wasn't relevant to the radon. One of the factors within household composition and disability, single parent households, doesn't really impact radon risk. But because the other three, youth, the elderly, and disability, significantly do, I decided to keep that theme in. So these are my maps using these three themes and overall. And so what you're seeing here is the way that they calculate it based off of the percentages of groups that have this vulnerability within each census tract, is they get a ranking from 1 to 4, 1 being low vulnerability and 4 being high vulnerability. And as you can see in my study area, each county in almost all the themes is predominantly 3 or 4, so high vulnerability relating to these themes. So that's just further information to me that once I've created this elevation risk map, I still do need to take into account the fact that a lot of the populations within my study area are also furthermore disproportionately impacted by radon risk, or could be based off of these parameters. And so this is just telling me this population does need to be served in this way, and I definitely need to continue to the next step, which is overlaying my social vulnerability rankings on my elevation parameters. So that'll be what I do next. And so I'm going to lay out my raster. Imagine this is happening in ArcGIS. And then I'm going to put my layers on top of it of the social vulnerability. And any area that is overlaid by a 3 or 4 in social vulnerability, the ranking that's underneath it based on elevation is going to bump up 1 for a combined ranking score. This is the best way I've come up with it so far. My methods may change a little, but so far that's what I'm doing. So any place that's currently yellow, but then gets overlaid by high social vulnerability will become orange. So that is what I'm going to be doing next to make my combined map. So in summary, when we use regional geology to generalize these radon hazards, we can potentially mislead populations by overlooking these local variabilities. And this is further confirmed by showing these elevated radium-226 measurements in my sediment cores in my counties of interest. And this paired with the at-home radon tests that show that this isn't all theoretical. These houses do in fact have high radon levels. This shows that there is a significant radon hazard in parts of the North Carolina coastal plain, even though it's been generalized as low risk for so long. And hopefully by pairing this social vulnerability information with these elevation-based parameters, we can best distribute resources for testing and mitigation for radon to the areas that most need it. So my next steps include what I talked about, combining my elevation-based risk zones and my social vulnerability rankings. I'm then going to put them together in a story map that tells how I got from point A to point B. You can interact with the different themes as well. And hopefully this will be a really interactive and easy to understand tool to guide local public health efforts. And then lastly, we are doing a sediment analysis, hopefully to find some or narrow down some of the sources of the radon within these samples. So this is what my sediment looks like these are both within the same core. One that has the lowest radium measurements, and then one that has the highest radium. Again, around once you got above 75 becquerels per kilogram, you got into high radium, and this is 128. So it's pretty high. And you can see the difference between low and high is incredibly significant. There's a lot happening within this sediment. There's a little pink guy right here. There's a bunch of rounded, there's a lot happening. And so we're doing analysis of this. We washed all the clay off. We're going to rerun it now to see if it was the clay that might have had this radium or if it's maybe the sediment. And then if it is in the sediment still, now that we've washed the clay off, we're going to further analyze what these different samples are. Okay. A big thank you to Jim, all the wonderful professors and professionals that have helped me through this, the Gamma Lab, family and friends, and all the Geo seniors that you see here and everyone else. So with that, do I have any questions?